All right, welcome to section 10.7, graphing linear inequalities. So linear equations, if we remember, a situation like y equals x plus 3, we would take that equation and we would use the y-intercept, 1, 2, 3, make a dot, and then we would use the slope. The slope is 1, so that's 1 over 1. We rise 1, run 1, rise 1, run 1. So we get 3 points, and that line would represent all of the solutions, meaning if we took this point right here, which is 2, 1, 2, 3, 4, 5, 2, 5, we plug it back into the equation, y equals 5, x equals 2, we would get 5 equals 5, meaning it's a solution. So that would be a true value. What if I pick the point 0, 0? If we plug 0 in for y, 0 in for x, we get 0 equals 3? No, that's a false value. And we know that any other point other than on this line would be a false statement, well, false point. That would give us, if we took that point, it would produce a false value, false value. However, anything on this line would produce a true value. And with equations, the line is the only boundary for contain only the true values. If I go to the right of it, I'm going to get a false. If I go to the left of it, I'm going to get a false. So it's a very small area. When we get inequalities, however, we are going to do the same thing. We're going to graph it in the same way, where we look at our y-intercept, which is 1. We're going to make a dot. We look at our slope, which is -1. So we're going to go down 1, right 1, down 1, right 1. And then we're going to draw a line. And that line represents some of the true values. And so what we need to understand is that from this point on, that line, in this case, because it's equal to, this is a very important understanding of when it's equal to, it's going to include the points on that line. Now, that line is going to separate true from false. So one side's going to be true, one side's going to be false. So if we test this point, let's take the point -5, 2. If we plug in 2 for y, -5 for x, we get 2 is greater than or equal to 5 plus 1, or 2 is greater than or equal to 6. Well, what do we know about that? That's a false statement. So this point on this side is false. And guess what? Every single point on this side is also going to be false. If one point is false, then all the points on that side of the boundary, of the line, will be false. Let's test another point. Let's test a point like 2, 2. So we plug 2 in. Y is equal to 2 minus, or the opposite of 2 plus 1. So we get 2 is greater than or equal to 1. And that's a true statement. So this point here is a solution. And guess what? Every point on this side is going to be a solution. So what we do is we shade the true side. We're always going to shade, because remember, these points represent true values. So what did we do with all these points? We shaded them by drawing a line. Well, now that it's an inequality, we're going to shade by doing these sort of long hairs, shall we say. So that boundary, that line, will separate false values from true values. When we have a single variable, we know that it's going to either be horizontal or vertical. So when it's one value, we know that x is going to cross, or the line's going to cross the x-axis at 1. Here's where it's 1, and we're going to draw a line. That is the graph of x is equal to 1, and now we have to test. And the easiest way to do this is test a point. If I test this point and I get, well, let's test it. So that point is 1, 2, 3, 4, 1, 2, 3, 4, 4. Negative 4, 4. What's my x value? Negative 4. Is negative 4 less than or equal to 1? That's a true value. So since I know that point is true, we know that this is the true side. So we're going to always shade the true side. So I'm going to draw those hairs. I don't have to test a point over here because I know that it's going to be false. So I really only need to test one point. We tested 2 here just to show that there was a difference. But from the point on, you don't have to test 2 points. You just have to test 1 point. So you test 1 point. If it's true, we know that that side is true. If it was false, we would know that the other side is true. So here's our equation. Again, we only have one variable. So we know that the line's going to cross the y-axis at 4. 1, 2, 3, 4. This time I'm going to use an open circle and dotted line. Can anybody tell me why that is? What's the one thing that's different this time? Notice it doesn't have an equal sign. So if I took that point right here, 0, 4, and I plug the 4 in, is 4 greater than 4? No, that would be a false value. Hence why it's open. It's an open circle. So this is still the boundary between true and false, but this time the boundary line is going to be false. This is the boundary line, and the boundary line is true because it's equal to it. So that's very important to understand, that when you have a greater than or less than, you're going to have dotted line and open circle for points. When you have greater than or equal to or less than or equal to, you're going to have a solid line and you're going to have a closed circle for your points because we want to include them. Don't include, include. Now we have to test a point. What's the easiest point to test? 0, 0. So let's test 0. Is 0 greater than 4? That is false. So we know this point is false, so we know the other side is going to be true, so we have to shade the true side. So we're going to shade the top side of that border. This is section 10.8.2, part 2. We are learning how to graph systems of linear inequalities. So we have equations, or we have inequality statements. We've got 2 of them, and because it's a system, we want to know what points they share. What points, multiple points, are true for both of those inequalities. So the first thing we do is we get our graph, and we're going to graph one of these equations. We're going to graph this equation first. It's greater than, so we know that my points are going to be open circle and my line is going to be dotted. My y-intercept is -3, so I have an open circle at -3. I'm going to use my slope, which is 2, up 2, right 1, up 2, right 1. And now I'm going to do a dotted line representing the border. I'm going to test the point 0, 0. Is 0 greater than -3? That is true. So I'm going to use my little hairs shading towards that true point. My next equation, I'm going to use green. And again, it's a less than sign. So I know in this example, this will also be open circle and dotted. I'm going to use my y-intercept, which is 6. 1, 2, 3, 4, 5, 6 on the y-axis. Open circle. I'm going to use my slope, which is up 2, right 1, up 2, right 1, dotted. Arrows on the end showing that they are lines. I'm going to test the point 0, 0. Is 0 less than 6? That's true. That was true too. And so I'm going to shade towards my 0, 0. I'm going to shade towards that true point. Now, what is the intersection of those two? The intersection is actually between here, not including the borders. So all of the solutions to both of these equations that they share is going to be in between there. These are parallel lines. This is a really fun problem I picked because it is unique in how it ends up being a nice sort of channel of solutions. And finally, part 3 of section 10.8, systems of inequalities, where it changes up a little bit. Before we were given equations and we had to draw the solutions. Now they give us the solutions and we have to write equations for it. So I'm going to do this line first, this horizontal line. I know that it crosses the y-axis at -3. So I know that it's going to be something like this. It's a horizontal line. It has one variable. It crosses the y-axis at -3. And now I just need to know I know it's shaded up. So I know that 0, 0 is true. So if I plug in that point, 0, 0, I have to make this statement true. What makes this statement true is a greater than sign. So it is a solid line, right? It's a solid line, so I know that it also has to have an equal sign. So the first equation is going to be y is greater than or equal to -3. Now I have to deal with my dotted line here. Well, my dotted line, first of all, I know that it's going to be either greater than or less than because it's dotted. It's not including the border. And it crosses the y-axis at -3. So I know my y-intercept is -3. We're using the form y mx plus b. My b is -3, so I substituted that in there. My slope is up 1, right 1. Up 1, right 1, up 1, right 1. So that's consistent. So my slope is 1. So I'm going to have x minus 3. And now I have to see this thing. Now there's two ways that you can do this. So it shades down. So I know that 0, 0 is going to be false for this equation. Just this one. Not this because it's shaded up. And it was true for that. But for this one, it's 0, 0 is false. So I could plug in 0, 0, simplify it, and then I have to be somewhat tricky, and I have to make it a false statement. Well, that would make it false, because 0 is not less than -3. So I could look at it that way, and I could write the equation, and this would be the solution. The other way is I could look at this equation, I can find a true point, which would be 1, 2, 3, 4, 4, -2, and I could plug it back into there and make it a true statement. So there's two ways of doing that. I kind of like using 0, 0 all the time. So if we have to write an equation for this graph, it would be y is greater than or equal to -3, and y is less than x minus 3. Really good question. Now we see that we have 3 problems. Woo! So let's take the vertical line. It crosses the x-axis at 3, so I know x is 3, and then I know that 0 is true. So if 0 is true, we have to use that. It's a solid line, so it's equal. So that's a nice quick way of writing that first equation. And now we have this line. It crosses the y-axis at 2, so my y-intercept is 2. Let's find my slope is up 1, right 2. Up 1, right 2 is 1/2 x. And then y, I know in this line it's shading down, so 0, 0 is true. So if I plug in 0, I get 0, 2, so it has to be this. It's including the border. So my second equation is y is less than or equal to 1/2 x plus 2. Let's do this equation. Crosses the y-axis at -1. My slope is down 1, right 4. So down 1, right 4 gives me -1/4 x minus 1. I know that it's shading up, so 0, 0 is true. So 0, negative 1/4, 0 minus 1, 0, negative 1. I have to make it true. It's also including, so I use greater than or equal to. And the system, for the equations for that system would look like that.